Hello everybody, welcome to a special ACEMS virtual public lecture, and this is about inclusion-exclusion in the mathematical sciences, who is kept out and how we can use maths to bring them in. So my name's Kerry Mangerson, I'm a Deputy Director and Chief Investigator with ACEMS, and I'm a Distinguished Professor of Statistics in the School of Mathematical Sciences at QUT, Queensland University of Technology in Australia. And I'd like to start by welcoming and or acknowledging the traditional owners of the land on which I live and work, and that's the Turrbal and Yagara people, the First Nations owners of the land where QUT now stands. And I pay my respects to their elders past and present, and Aboriginal elders of other Indigenous communities who may be online with us today. We'll be taking Q&A questions and following Dr. Cheng's presentation. So please use the Q&A button on the bottom of your screen to participate. Please ask questions. We'll have a presentation from Dr. Eugenia Chang, and then we'll also have the questions after. So this is your opportunity to participate as well. I'm delighted to welcome Dr. Eugenia Cheng, who's going to be presenting today. So Dr. Cheng is currently a scientist in residence at the School of the Art Institute of Chicago and honorary visiting fellow of the City of the University of London. She's previously a senior lecturer or associate professor for us of pure mathematics in the School of Mathematics and Statistics at the University of Sheffield, UK. Her research is in category theory, mostly higher dimensional. So Eugenia has written a number of books, and in addition to her latest book, X plus Y, a Mathematician's Manifesto for Rethinking Gender, published in 2020, she's the author of several popular mathematics books: How to Bake Pie, an edible exploration of the mathematics of mathematics; Beyond Infinity, an expedition to the outer limits of mathematics, which was shortlisted for the Royal Society Insight Investment Science Book Prize; and The Art of Logic, published by Profile and Basic Books in 2018. Phew, a busy schedule. Eugenia has appeared on The Late Show with Steven Colbert. She's been featured in the New York Times, and she's presented TEDx talks. And today, she's talking to us. Dr. Chang, welcome, and thank you for joining us today. I'll hand it over to you.
Thank you so much. Well, thank you everyone for being here today. And thank you especially to everyone who's been involved with organizing this event. I'm very excited to be talking to you. I'm sad that I can't actually be there in person, but it's very important for us all to do what we can to keep the community safe. And I appreciate that technology has made this possible, even though I'm sure we're all a little bit fed up with staring at our screens all day. So thanks for taking the time to stare at the screen with me on it today. I am going to talk about inclusion-exclusion in the mathematical sciences. And I want to talk about my experience as a woman in mathematics, but also I want to draw on my expertise as a mathematician. So my theory for how we can make progress on these issues draws on both my experience and my expertise. And that's what I'm going to talk about today. So first I will talk about what maths is and how it can help us. Why could maths possibly help us sort out gender questions? And I'm not talking about just quantitative maths. I'm not talking about statistics and statistical analysis. I'm talking about abstract maths. So I'm going to talk about character and gender and how we can escape what I perceive as being a one-dimensional gender trap when we think about matters of gender imbalance. And then I'll talk about what I mean by more inclusive maths. And then in the second part, I will introduce my field of research, category theory, and I will not be basing this on any prior knowledge of anything. This really is an introduction to the ideas of category theory. So first I'll talk about what category theory is, and I'll talk about how it focuses on relationships between things and how it gives us a more nuanced way of talking about sameness. And I'll relate all these things to what I think we can do about gender imbalance in mathematics to bring more people in who are currently being excluded. First of all, what is maths and how can it help? Well, there's a traditional view of pure maths that says that pure maths is very, very far away from real life, and that it's only really relevant to applied maths, and applied maths is relevant to science, and science is relevant to engineering and medicine, and engineering and medicine are relevant to that part of the human world. It's a quantitative part of the world that is driven by numbers and equations. And this is all very well, and I used to think that that was the only way that my research would ever have any effect on real life. But this is very narrow. And one of the problems with this view is, apart from that it's not really accurate, another problem is that it gives people a chance to take themselves out of maths, because they can say, this is great, I'm very glad somebody does maths, but I don't need to do it. Because if you don't think, if you know you're not going to go into any of those fields, then you can just say, well, I don't need maths, why do I need it then? And I think that there's more to maths than that, and that's why maths education is so important. And I do think that maths is really important as a central part of education. And I think it's because pure maths is really about how to think. And therefore, it is really relevant to the entire human world, at least the part of the human world that thinks. Sometimes it seems like not all of the human world is thinking, but wouldn't it be nice if everyone could think a little bit better? And to me, that's what pure mathematics is about. It's about how to think about the world around us. And that is how I use it in my daily life. I don't use quadratic equations or trig in my daily life very much, but the discipline of pure mathematical thinking is something I use all the time. So it can help us. How can it help us? Well, sometimes all it takes to gain insight into a situation is a slight shift in perspective. And sometimes that's all that pure math does, but that slight shift in perspective opens up whole new thoughts and whole new patterns that we didn't see before. And one of my favorite instances of this is if you go up to the top of the Hancock Tower in Chicago, which is actually not called the Hancock Tower anymore. But if you go to the top of the building formerly known as the Hancock Tower, which is pretty tall, then if you look across the city of Chicago, which I haven't obviously done for more than a year, then it looks like a huge mess. But then if you just slightly shift your angle, then all the buildings line up and you see that it's a grid. And so I wanted to take a photo of that, but I haven't really left the house for the last 14 months. So here is my Lego version of the Chicago skyline. And if you look at it from this angle, then it doesn't really look like very much. But then if you just rotate it a little bit, then you can see that everything lines up. And I'm going to propose a theory to address gender issues in mathematical sciences and beyond that is really just a slight shift in perspective. But to me, it has opened up so many possibilities for how to make progress and do things differently and better. And what I want to talk about is how to escape the one-dimensional trap that I think we're in. And this one-dimensional trap is a trap where we think of gender as a one dimension, that there's masculinity at one end. I should point the opposite way because of Zoom. So wait, yes, there's masculinity at one end and there's femininity at the other end. And we have arguments about whether masculinity is good, whether femininity is bad, whether everyone should try and be more feminine. And so in those arguments, the pressures on women are that, well, men are more successful because of their masculine qualities. And so we ask women in the name of equality to become more masculine in order to be successful. And then there's a reaction against that where some women really like being feminine. And then for men, the pressures go in the opposite direction, because the pressure of equality is that men should become more feminine and they should learn to get in touch with their emotions and become empathetic and look after children. And then there's a reaction against that, which pushes men to be more masculine, which gives rise to toxic masculinity and people saying that there's a war on men or something like that. And I think that all of this is the wrong approach, because we are in this process here, we are relating character types to gender in a way that is obstructive. Some people think that it is just descriptive, but I think it has become prescriptive. And in that way, it is obstructive. And so I have decided that we need some new terminology to think about these things. And I have come up with these words: ingressive and congressive. Ingressive to signify the character of going into things and being an individual and not worrying about the people around you, and congressive to signify bringing people together and nurturing people and thinking about community. And the first thing I want to stress is that this is not a straightforward dichotomy. I'm not just trying to move from one dichotomy to another. I'm trying to characterize different kinds of behavior in different situations. And in a way, it's more of a two-dimensional thing. I am a higher dimensional mathematician, so I like thinking in higher dimensions to escape low dimensions. And I think that this red and blue square, I like the idea that if red is ingressive and blue is congressive, then what happens is that up in the top left corner, you are very red, which is very ingressive. And then at the bottom right corner, it's very blue, which is very congressive. And then towards the middle, it merges and you can be a bit of both. But you could be a lot of both, or you could be not very much of either. And crucially, you can move around this square. It's not fixed. I'm not saying this is anything biological at all. And this is what my particular journey has looked like, I think. Because what I used to say is that when I was a normal career academic, I tried to hide all signs of femininity in order not to give anyone a chance to stereotype me and say that I couldn't do it because I was a woman. But then when I achieved tenure, and I felt more secure, I tried to get in touch with my femininity. And I first only did that outside work. And then I wanted to do that at work as well. And then I discovered that I couldn't do it and that I didn't like my job and that I left. And since then, I've been thinking about this and thinking, well, that doesn't make any sense because I identify as female, so everything I do is feminine. And what makes much more sense is to say, I learned to be as ingressive as possible because of the ingressive academic environment. And I realized that I didn't like myself like that. And so I left and I tried to unlearn that and become as congressive as possible. And it's still a journey because I think society has been filtering, has been rewarding ingressive behavior for so long that we've all learned to be as ingressive as possible in all circumstances. Practically all circumstances. And it takes some time to unlearn that. But I do think it's learned behavior and that therefore we can unlearn it and become more congressive. So before I talk about how to do that, I want to say more about what these things mean. And I first want to stress again that I'm not trying to classify people into different parts. I'm not going to make some kind of questionnaire to classify who is ingressive and who is congressive, because it's not fixed and it's not a clean dichotomy. It's a descriptive characterization of behaviors and interactions. And because it's quite abstract, we can use it at a lot of different levels. We can apply it to individual people, individual interactions. We can apply it to broader society. We can apply it to the way we teach, classroom behavior, political systems, voting systems, or we can zoom right in and apply it to individual mathematical activities and toys and games. And so what I mean by ingressive is focusing on oneself and imposing on people. It's independence and individualism. It's being competitive and adversarial and selective or single track in your thinking. Whereas being congressive is more about being circumspect, collaborative and cooperative. It's about interdependence and connectedness, taking others into account and focusing on society and community. And often in these very polarized political times, especially polarized in the US, I often sit down and think that the root of the differences is so often that someone is taking more account of the community and considering us all as part of a community, and someone else is thinking of everyone as individuals and thinking adversarially, which comes down to some people being ingressive and some people being congressive in the way they think about the world. And I think that congressive behavior is much more productive for society. And yet we have been rewarding ingressive behavior for a really long time. So I am not advocating that we should completely forget about gender. I'm not advocating gender blindness. I think that there are issues of genuine gender bias, direct gender bias, like misogyny directly. And then there are issues of character where we are nurturing inappropriate character types for what we're trying to achieve. And I think there's a two-dimensional thing again. And if we only address issues of character and forget about gender, then what we're doing is we're being gender blind. And if we are gender blind, that might sound terribly idealistic. And in the end, eventually, I would love us to get to a world where we can be gender blind. But we can't at the moment because there is still direct gender bias against people. And we can't correct for it if we ignore the existence of gender issues. On the other hand, if we only address gender and we don't address character, then what we're doing is we're doing diversity without inclusion. We will increase the numbers of women in situations, but we won't actually change the atmosphere that was previously keeping them out. And we will also get accused of reverse sexism. So of course, if we do neither of these things, then we are maintaining the status quo. And I hope that we don't want to maintain the status quo, because very few people benefit from the status quo. Those people will try very hard to hold on to the power that they have, but the rest of us are not benefiting from that situation. And so here is where I think progress is. If we use character to address character and use gender to address gender, and importantly, we must address all forms of bias and exclusion, including bigotry along dimensions of race and along dimensions of gender presentation and exclusion of trans people and all the forms of exclusion. I think that if we could become more congressive, then we will be becoming more inclusive in all ways. Here in particular is how I think we can go from ingressive maths to more congressive maths. And I think that we have typically presented maths in education very ingressively, and that keeps some people out who are put off by that. And I came to think of this in particularly sharp relief when I moved from teaching maths to maths majors at the University of Chicago. I moved from there to the School of the Art Institute of Chicago, where everyone is an art student and typically was very put off maths at some point in their past education. Also, the maths classes at the University of Chicago were very heavily male-dominated, more than 90% male-dominated. Whereas the classes, I still teach maths, but it's to art students, and those classes at the School of the Art Institute are not male-dominated at all. Men are in an extreme minority, and they are, in fact, I typically have more trans students than cis white men in my classes. So the cis white men are in an extreme minority, but still somehow manage to dominate the situation unless I take very active steps to neutralize the ingressivity and nurture congressive behavior. And everyone has been so conditioned by society to be as ingressive as possible. But I think that when I try and neutralize it, it turns out most people don't really want to be like that. It's learned behavior and we can unlearn it. And in maths especially, many people have been very, very conditioned to have an ingressive approach to maths. And ingressive maths is about outcomes. It's about facts and rules and solving problems and calculating answers. It's about traditional lecturing where someone stands at the front and spews knowledge in the direction of students. It's about right and wrong answers and exams and competitions. Whereas congressive maths is about process. It's about investigation, building structures, uncovering relationships. I love project-based learning rather than traditional lecturing, where you do a project that incorporates all sorts of things. I love low-floor, high-ceiling projects, where there's a very low barrier to entry, but practically no limit to what you can learn from that situation. And instead of exams and competitions for outreach, I love festivals and fairs. I hate maths competitions. In fact, I hate all competitions and I hate all competitive situations. Whereas I love festivals and fairs. And if someone had put me in for a maths competition when I was a teenager, I would have hated it. And I would have concluded that I shouldn't be a mathematician. But actually, I'm a very good mathematician. And I dread to think of how many other congressive people we have put off maths by the competitions in school. So I prefer festivals and fairs of the kind where there's no particular aim, but there's just loads of stuff that you can do and you can wander around and explore and discover as you like. And here is one of my favorite relationships to uncover. It's a bagel inserted into a slinky. This is quite a profound fact in the field of algebraic topology, showing that a torus, which is the shape that is the surface of a bagel, is the same as the product of a circle with itself. But it's so enormously satisfying, to me at least, to insert a bagel into a slinky. It's just really fun and it's memorable and it's satisfying. And that's the kind of maths that I think is congressive and that sparks the imagination of my congressive art students who were put off by the ingressive form of maths that they had before. And one of them said at the end of the semester, I always ask them to reflect at the end on how their view of maths has changed across the course of the semester. And one of them said, now I find that maths is not just a tool, and the real reason for learning maths is to practice our thinking. And I loved that, because that's what I want to show them, that it's often a tool, and often a tool just for exclusion, actually, that it's there precisely to filter people out, to have exams that will declare who is better than who, so who should go into university to do what. Whereas I prefer bringing people in. I'd now like to move on to category theory and introduce what I think is congressive about it, and how it can be a congressive form of maths that can bring people back into maths who have been excluded or felt excluded. And I do this with my art students, despite the fact that category theory is traditionally thought of as high-level abstract maths that you don't do until you're probably in grad school or a very advanced undergraduate maths student. So here are some ways in which I think category theory is congressive. It's about making connections between different ideas. It's about understanding structure more than problems and answers. And it focuses on relationships between things. And it gives us different ways in which things can be the same or not. And I think that's really crucial, because it focuses on relationships rather than intrinsic characteristics. And that's what I like to do about people. I like to think about how people relate to each other. And this is where I thought about the terms ingressive and congressive. Because if we think about something intrinsic about them, then that's not really that relevant, because we're assuming there's a link between something intrinsic about them and the way they behave. Just like when we assume that if somebody is a man, they will behave in a particular way. And with this new ungendered terminology, we can escape that and really focus on how people relate to each other instead. I like to say that category theory is the mathematics of mathematics. And in order to understand that, I need to tell you what I mean by mathematics in the first place, which is that I think that mathematics is the study of how things work. But it's not the study of how any old things work. It's the study of how logical things work. And it's not any old study of how logical things work. It's the logical study of how logical things work. And the trouble with that is that nothing actually does behave logically. And that's why we go abstract, because the move from the concrete world to the abstract world is one where we ignore the pesky details that get in the way of the logic. And we think about the an idea of a process instead. And there we can apply logic. And although it's not precisely the real world we're studying anymore, the concrete world, what we're doing is we're studying the principles of the concrete world. So we're understanding something at its core. And I'm going to show that one of the points of doing that is that we can then apply it very, very broadly when we put the details back in. Now, if category theory is the mathematics of mathematics, then what I seem to be saying is that category theory is the logical study of how logical things work, which sounds very looped up on itself. But I'm going to show that rather than simply being far away from concrete life, this actually gives us ways to think about issues in life that I really care about, and certainly that my art students really care about. Because I think education, when it's at its best, is not just a one-way process of someone lecturing at students, but it's a process in all directions where everyone learns from everyone else. And I've learned so much from my art students, and I think it's really important to understand what motivates your students in order to tap into that motivation, to connect with them, rather than impose your motivation on top of them. And my art students are, I think what I found is that the thing that really motivates them is social justice, that they're doing art because they want to make the world a better place. And so I found all these ways in which I think of the world in that way, the social justice questions of the world through the lens of category theory. And that got them interested in this very abstract branch of maths. So first of all, I say that pure mathematics is a theory of analogies, because, for example, if we look at two apples and two bananas, we might go, those things have something in common with each other. And what is it that they have in common? It's that they're both two things. And so we make an analogy, but we don't just say two apples and two bananas are analogous, which is what we kind of do in normal life. We actually make precise the thing that we are considering to be the analogy, and then we study it in its own right. And that's how this analogy becomes the concept of the number two. And so we move from the concrete world into the abstract world. Now, there are different analogies that we could make between these things. We could, for example, say that they're two fruits, and that's a perfectly valid analogy. It's a little bit more concrete because it's closer to the real world than just two things. But the trade-off is that we can't include quite as many examples anymore. For example, we can't include two chairs at that point. And to include two chairs, we therefore have to go further up to the level of two things. So see, although the level of abstraction takes us further away from the concrete world, the point is to bring in more examples. Here's a more profound example, that 1 + 2 and 2 + 3 are both examples of A + B. And sometimes, well, often people say to me, I was fine with maths until the numbers turned into letters. But I'm going to show that the point of turning things into letters is to be able to bring in more examples. Now, if we say that 1 × 2 and 2 × 3 are both examples of A times B, then we can go one step further. We go, oh, wait, A + B and A times B are both examples of A thing B. And that's called a binary operation. And what we've got here is a series of progressive levels of abstraction that we often encounter as we progress through maths education. So the bottom level is like elementary school arithmetic, and the middle level is where you start doing algebra, and the top level is what we study in abstract algebra, which you might do if you go to university to do maths. And there's another level. There's another level, which is this A circle B, which is the notion of general composition of things. And that's a level further. We can now encompass all sorts of things, practically the entire of maths. So don't worry if you don't know what these things in maths mean. I'm just trying to show that it's practically the whole of maths: functions, relations, matrices, homotopy, and indeed life. And category theory, that point is where I think category theory is, the top level of this. So category theory is considered to be very abstract. And it came along in the middle of the last century and was originally just used to study some particular aspects of topology. But it has gradually been shown across the last 60 or 70 years to be fruitful in more and more places that are further and further from where the original applications were. And I use it to think about life as well. Here's another example of an analogy where what do puff pastry and viruses have in common? Well, what they have in common is that they're both governed by exponentials. And so sometimes that level of abstraction, if mathematicians study it at that abstract level, and then it helps everyone to understand what's going on. And we saw, unfortunately, during this pandemic, that some people were able to understand exponentials and therefore understood that even when the virus didn't seem that bad, it was going to get bad if we didn't do something about it. Whereas some people didn't understand exponentials. And so they thought, well, it's not that bad, you're just all fear-mongering. Another way in which analogies have caused contentious arguments is that some people think that COVID-19 is just like seasonal flu. And this is where mathematics is more precise than arguments in normal life, because we don't just say things are like each other. We make precise what level of analogy we're taking. And I think it's important to note that whenever people have arguments about analogies, there is a sense in which things are analogous, and there is a sense in which things aren't analogous. There is no correct level of abstraction. And my wonderful supervisor, Martin Hyland, taught me that the aim of category theory isn't to find the highest possible level of abstraction. The aim should be to find a good level that's appropriate and illuminating for what you're trying to do right now. And so, yes, COVID-19 and seasonal flu are alike in that they are both contagious viruses causing respiratory illnesses and fatalities. But COVID-19, as we know, is different because there's no herd immunity. The vaccine is new, and we do not yet have very good, well, it's getting better all the time, but we still have incomplete scientific understanding. And I think it's more productive to point out the different levels of abstraction going on in those analogies, rather than just to keep yelling backwards and forwards about someone being wrong because these things aren't the same, when they can just go, well, they are the same. The idea of category theory is that we can study things via their relationships rather than via their intrinsic characteristics. And this was a shift that happened in the middle of the last century and that has really taken hold in mathematics. And we draw relationships in category theory like this with an arrow. So this is some kind of relationship from A to B. And it's an arrow because relationships don't necessarily have to go both ways. For example, A is the mother of B. B is not the mother of A. But B has a relationship with A, but it's different. And then if B is the mother of C, we can then deduce something from that situation, which is that A is the grandmother of C. And similarly, if we observe that white men are more privileged than white women, and if we observe that white women are more privileged than black women, then we can conclude, we can deduce that white men are quite a lot more privileged than black women. And this is called composition in a category. And composition means that we can omit arrows that can be deduced from the situation. So we can omit these red composite arrows because we can deduce them from what's going on above. A little bit of history about category theory. Previous to category theory kind of generalizes set theory. Set theory came before category theory. And the idea of set theory is based on membership in sets. They're both foundations of they're both foundations of mathematics, which means trying to understand the fundamental principles going on in mathematics. And set theory starts with the basic idea of things being members of sets, whereas category theory starts with the basic idea of looking at relationships between things. And then in set theory, equality is therefore based on intrinsic characteristics, whereas in category theory, we have a notion of sameness that is based on the roles that things play in context relative to the other things in that context. And so things don't have to be equal based on intrinsic characteristics. And I think this is really important because we can get really distracted by the fact that men and women are in fact different, because if they weren't different, then we wouldn't have the words men and women at all. But they can play the same roles, and that's what the point is. I think it's to focus on what roles they can play. And I think that's more inclusive because then everyone can kind of decide what roles to play and learn what roles to play. It's kind of like the idea of a club where one club might just be based on some intrinsic characteristics that you can't change about yourself. Whereas if another club is based on people who care about children, for example, then that's, I think, more inclusive because everyone can decide that they care about children and then join that club. So in set theory, we just have sets which consist of some objects, and that's it. In category theory, we have some objects and some relationships between them that gives us the context we're thinking about. And they satisfy some axioms, but I'm not going to go into that. I want to give an example of how thinking about relationships between things can be very productive. I'm going to start by thinking about the factors of 30. So maybe we can just remember what the factors of 30 are. They are 1, 2, 3, 5, 6, 10, 15, and 30. It's not very interesting. It's a bunch of numbers in a straight line. And I like to say that we live in a three-dimensional world, so we write on two-dimensional pieces of paper in one-dimensional straight lines. So we stuff our thoughts into a one-dimensional straight line when maybe they don't want to be in a one-dimensional straight line. Maybe they have natural geometry in higher dimensions. I like to say this is why I don't tidy the papers on my desk, because they have natural geometry in higher dimensions. Anyway, I'd like to exhibit some of the natural geometry of this situation by thinking about how these factors are related to each other. And I'd like to draw a kind of family tree showing which factors are factors of each other as well as being factors of 30. So 30 goes at the top like a kind of great grandparent. 6, 10, and 15 go directly into 30. They're like direct descendants with no generations in between. Now 5 comes from 10 and 15. And we don't need to draw a line from 30 to 5 because we can deduce it by composition. Just like when we're doing family trees, we don't have to draw the generation from grandparents to their grandchildren because we can deduce that through the single generation arrows. Now 2 is also a factor of 6 and 10, 3 is a factor of 6 and 15, and 1 is a factor of 2, 3, and 5. So now we see that it's the corners of a cube, which I think is a lot more interesting than just a bunch of numbers in a straight line. And if a bunch of questions come to your head, then you're thinking like a mathematician. If you think, why did that happen? Do all numbers make cubes? What happens with other numbers? What other shapes can we get? So the reason that this number makes a cube, and maybe you've started to see it, is that the bottom three numbers above 1 are 2, 3, and 5, and they are the prime factors. Remember, a prime number is one that has no factors other than 1 in itself, and 1 isn't prime because, well, 1 is at the bottom here. It doesn't do anything when we multiply. 2, 3, and 5 are the prime factors of 30. And then 6, 10, and 15 have 2 prime factors each, and 30 has 3. So what we have is these sets of factors at prime factors at each corner. So we have at the bottom, we have the empty set, that's the empty set sign. And then we have the sets containing 1 element, and then we have sets containing 2 elements. And then at the top, we have a set containing 3 elements. So this has now just become a diagram of sets and their subsets. Subsets are sets that sit inside other sets. And each arrow shows kind of throwing out one element of the set. And then you can go, oh, well, this structure doesn't really depend on what those numbers are. So we could just call them A, B, and C. See, I've turned the numbers into letters. And now that they're A, B, and C, I can immediately take A, B, and C to be some other numbers, like say 2, 3, and 7. 2 times 3 times 7 is 42. Here are the factors of 42, and then I can build up the diagram. I'm going to build it up from the bottom this time because I've now understood that it's to do with the prime factors. So 2, 3, and 7 go first, and then we have those that are a product of 2 prime factors, and then we have 42 at the top. And if we draw the other diagrams out, the middle one is analogous to the one on the previous slide, but with every 5 replaced by a 7. And when we go up to the level of letters, it's actually the same diagram now. We don't have to say it's analogous because this is the thing that is causing the analogy. It's a set of 3 things and arrows showing the loss of 1 thing each. And now I want to say what the point is of turning these things into letters, because it means we can apply this very broadly. It doesn't have to be prime numbers. It doesn't even have to be numbers. It could be 3 types of privilege, such as rich, white, and male. And then we have arrows depicting the loss of 1 type of privilege at a time, which gives us rich, white, rich male, and white male. And then we have people with just 1 of those types, rich, white, and male. And then at the bottom, people with none of those 3 types of privilege. And so if I put the missing words back in, we have rich, white, non-male people, rich, non-white male people, non-rich, white male people, and so on. And at the bottom, we have non-rich, non-white, non-male people. This diagram depicts direct loss of privilege 1 at a time. And I think it's really important and indeed illuminating, because it's this diagram that I think is what privilege is about. Whereas some people think that white privilege means that all white people are better off than all non-white people. And so they do things like point at some super rich black sports star and say, look, there's a rich black person. That means there's no white privilege. But that's not what white privilege means. It means that if you hypothetically lost just that one characteristic about yourself, we would expect you to be worse off in society. Or if that rich black sports star had all the same qualities about him but were white, then we would definitely expect him to be better off in society. Because, for example, he wouldn't have to fear for his life every time that he was stopped by the police or saw a policeman somewhere. This diagram of interactions is very widely applicable. So here's another situation which depicts really terrible arguments about why men are dominating various situations. And sometimes the arguments to justify there being more men in situations are so flawed that it can be really hard to pin down what the flaw is, because there are too many flaws. So here's a diagram of 3 types of flaw. And what happens is that something reasonable happens at the top, which is that men are observed to be generally something or other, Y. And then somehow we slide down through these arrows to get to this bottom thing, which declares that men are by nature, biologically, always this other thing, Z. So perhaps we're trying to understand why there are more men math professors in the world. And so we start at the top, and there's some observation that men are observed to be generally more, I don't know, self-confident, let's say. And then somehow we go from there to declaring that, well, that means that men are by nature destined to be better at mathematics. And you go, wait, what happened? So there are 3 types of sneaky slide argument going on here, where we're replacing something reasonable with something that is not equivalent to it. In this direction, we are taking an observation and we are sliding from there to pretend that it's something biological and innate. In this direction, we're taking something that is generally true, and then we're sliding from there to believing that it's always true. Whereas in fact, things that are generally true don't apply to individuals at all. And in this direction, we're taking some characteristic Y that we think is related to Z, and we're declaring that because some characteristic Y is very observable, then this must determine the Z as well. And that's often a really huge leap. And sometimes it's things like experiments done on babies showing that newborn babies, so you have to do these experiments on newborn babies to be sure that something you're doing is biological and not just society's pressure. But then the experiment says that it looks at how long a baby looks at a different picture. And one of the pictures is of a human face and the other one is of a mobile or something. And then because the boy babies look at the mobile for ever so slightly longer, this is determined to be something about their brain that means that they're going to be better mathematicians, math professors. And you think, wait, how did that green slide happen? And when you put these all together, you get this amazing three-dimensional structure of bad arguments justifying gender inequality. I want to finish by talking about what I think we should do about sameness, inspired by what category theory does about sameness, so that I'm not just talking about bad arguments and I can talk about good things as well. We think that mathematics is all about equations, but you know what? All equations are lies. Let's have a look at these two. You might think they're true, but only the answers are true. The things themselves aren't actually equal. If you help a small child to do arithmetic, which I love doing, if they're at the stage where they're still counting in their head, if you ask them 8 plus 1, they'll put 8 in their head and then count on by 1 and get 9. Whereas if you ask them 1 plus 8, they'll put 1 in their head and then try and count on by 8. And if they're not very good at it yet, they might get confused along the way or bored and not get the same answer. So the whole point about this is that 8 plus 1 is easier than 1 plus 8. And we benefit from this equation by knowing that if we only care about the outcomes, then we can use the easier process to get to the outcome. And so the whole point about this equation is that there is some sense in which the two sides are different, as well as some sense in which they're the same, and that benefits us because we can kind of pivot using the sense in which they're the same to progress from the sense in which they're different to the other. And this is the same with 2 times 5 and 5 times 2 as well. 2 times 5 is 2 packets of 5 cookies each. And 5 times 2 is a waste of plastic. Okay, not all equations are lies. The only equation that is not a lie is x equals x. But what's the use of that? That equation is completely useless. So all equations are lies or useless. So what category theory does is it says, well, since all equations are lies anyway, we can choose senses in which things are the same, and we can choose what we want them to count, which things we want to count as the same. And we do that in category theory using the notion of invertibility. So, for example, if we do addition of 4, we can start from 1 and add 4 and get 5. And we can invert, that is, we can undo that process by subtracting 4. Whereas, if we square a number, that's a bit more tricky, right? If we square -3, we get 9. But can we undo that process? If we try and undo it, how do we know we're going to get the negative square root and not the positive square root? So that is more tricky, and that's what invertibility is about. And in category theory, we express this by saying a pair of inverses for each other is an arrow going in one direction and an arrow going back again, such that when you compose them from A to A, that id stands for identity, which means it's like not doing anything. And if you compose the other way around, it's also like not doing anything. And so it's like if you freeze water and thaw it again, you've just got water again. It's like you didn't do anything. Whereas some things, when you freeze and thaw them, they come out a bit differently. If you freeze cheese and then thaw it again, it might be much crumblier than it was before. And if you freeze milk and thaw it again, then it might separate. And so what we want is to be able to go there and come back and it be sort of like we didn't do anything. But that doesn't mean that A and B are actually the same, but category theory then regards them as the same. A and B are called isomorphic, and that is the more nuanced notion of sameness that we use in category theory. So isomorphic objects are treated as the same by the rest of the category, even though they're not literally the same. And here is why they are treated as the same. And this is the most technical part of the talk because we're coming to the end. So this is some quite technical, profound category theory here. If I have a pair of objects A and B and inverse arrows between them, now I'm going to imagine another object X looking at A and B. Now remember that categories only see the relationships between things. They don't see the intrinsic characteristics. It kind of reminds me where I've got to in my life, where I don't think about what people look like really at all. I don't understand what it means to look at a photo of someone and say that they are beautiful. Because to me, I really do see beauty as just how people behave and whether they are kind and generous and respectful and nurturing. To me, that is beauty. It's nothing to do with what someone looks like. I know that sounds a bit idealistic, but you know what? I am idealistic. So categories only see how things relate to each other. So if X, this object X, is looking at A and B, well, every relationship X has with A, we can compose with F, and that will produce an analogous relationship with B. And conversely, if X has a relationship with B, we can compose it with G, and that will produce a relationship with A. And what this is saying is that the relationships X has with A exactly match the relationships X has with B. And that means that X can't tell A and B apart because X only sees relationships. And that means that the relationships A has with the rest of the category are the same as the relationships B has with the rest of the category, which means that they can play the same role in that category. And I think that this is a really important way to treat sameness and equality in the rest of our lives. Because I think equality doesn't mean people are the same, because no one is actually the same as anyone else, and that's wonderful. But equality, as we talk about it in life, is about when the world should treat them the same, because they can play the same roles in that particular context. And that is something that a thought I have come to inspired by the notion of isomorphism in category theory. So that is all the category theory that I thought I'd show you today. I want to finish with a call to action about what we could do in both maths and life to nurture a more congressive and therefore more inclusive world. In maths, let's teach more congressive maths, and let's teach it more congressively and nurture congressive behavior in classrooms. And I think that category theory is an example of congressive maths that works at many levels, not just at graduate level and undergraduates, but I think that it could be taught in high school as well, in the same kind of way that I teach it to art students, as a way of thinking, not necessarily as a rigorous technical tool for doing further mathematics. And in life, let's nurture more congressive behavior, and let's build more congressive environments at all scales and all levels. And the good thing about this is that we can start small. We can start in our personal interactions with our friends and with other people. And we can do this with our families and in our family dynamics. If we teach, then we can nurture congressive classroom environments. If we are a head of a department, we can nurture congressive department. If we run a business or a theatre or a company, then we can try and nurture congressive behavior. And then I think we can gradually build up to broader society. And I really believe that we can work together to make a more congressive world in maths, in education, and beyond, and that this will be better for everyone of all genders. Thank you very much.
Thank you very much. That's a fantastic seminar. Thank you. Great ideas and lots of very thoughtful comments there. And we come to the Q&A part of the seminar or the session. And we've had a few questions, and so I'd like to just pick some of them. We can't go through all of them. I'm sorry to the people who've submitted them. I will send all of them to Eugenia, and perhaps she can make some comments on them as well. But we've got a couple here, and I'll start with one of them, Eugenia, and some of it's about the sort of the early part of your discussion, and then the later part. And the first part is about this idea of ingressive and congressive, and you sort of set it up to be in some way in opposition to each other, and so almost in one dimension. But then you drew it sort of in two dimensions. And so one of the questions is about how to think about that. Is it sort of in two dimensions? Is it in one dimension? So I'll pass that to you.
Thank you. I think it's in many dimensions, and I really didn't mean to set it up as a dichotomy, and I really don't think of it as a dichotomy. It's really in different directions. And so, for example, competitive and collaborative aren't really in opposition to each other. The opposite of competitive is non-competitive, and that's different. And so I think they're just different. They're sort of like orthogonal things going in different directions. Some of them were a bit more like things in opposition to each other, because maybe being individualistic is the opposite of being community minded, but I don't think it's quite like an opposite. It's just doing something different on a different sort of scale. And I think that it's important to note that, as I said, these things aren't biologically determined, and that they're not fixed. So you can move around and you can do different things at different times and be different things in different situations. But when I say it's not a dichotomy, what I mean is that we don't separate humans into two different categories. The notions are sort of in opposition with each other, and I think that that's okay, but we don't have to divide humans into a dichotomy like that.
Right. Okay, thank you. And this idea of ingressive and congressive, and that there's not really a dichotomy. There's other theories like this, and one of the participants has asked about Hofstede's theory and the idea of social orientation and so on. So, do you have some comments about like where your ideas sort of sit in the broader context of these kinds of theories?
Yes, I think that there are many ideas that lead into this, but what I'm trying to do is what pure mathematicians do, which is link many ideas together into one concept that works at different levels, because usually those other theories are about one level. They're about society, or they're about human interaction, or something like that. Whereas because my approach is more abstract, it works at all those levels. And so, for example, yes, there is this concept. I don't know what that was. It's actually a little bit ingressive to throw around fancy names of theories. But there is the idea of social dominance orientation, which is the idea of people who are really consumed with the idea of hierarchy in society, and that they need to dominate. And that is very related to ingressive behavior, I think, but you can't really apply that to, for example, a mathematics outreach activity, because you can't really apply it to a math homework question. I don't think that it's abstract enough to apply at all those levels. Whereas I think you can think of an ingressive math homework question, which is one that is very focused on an outcome rather than a process. It's about the answer, and maybe this is related to the social dominance thing. It's about testing to see whether a student, or to see whether a student has succeeded or not. And it's that idea of evaluating in order to filter people out, which I don't think is quite the same as social dominance, but it is to do with hierarchies more generally. And so I think that this is where having a more abstract concept can really help, because once you have a place to put it in your brain, it unites so many different things.
Right. So following on from that then, one of the participants asked, like, what are your favourite questions that can identify whether a student has really understood some levels of abstraction? So do you have any like favourite questions?
Well, there are many things I like doing, but mostly I just like talking to students. I don't test them. I think that sounded a bit like, how do you test whether a student has really understood?
I think it's more like just like, how would you ask them or probe them?
Well, we have a conversation. We have a conversation, and I ask them to think about how it relates. So often it's that I ask them to think about how this concept relates to things they've experienced in their own life. And so some of the homework questions I set are writing homeworks, where I ask them to think about, for example, when we may be talking, I think this is a fairly mathematical audience, but we talk about ordered sets, which are sets that come with some ordering, and then we talk about functions that preserve or don't preserve that ordering, and that those are order preserving functions. And I asked them to think about where those kinds of hierarchies are antagonistic in life, and they come up with wonderful examples. And just this semester, a student came up with a fantastic example of a non-order preserving function, which is triage. Because the whole point of triage is that people arrive in an emergency room in some order, but you shouldn't treat them in that order, because you should decide who's more urgent. And then the whole point of triage is to change the order so that they get treated in order of urgency rather than in order of arrival. And I just thought this was a fantastic example of a non-order preserving function that is good for us. And actually it was better than my examples, because all my examples were where non-order preserving functions are bad, where things like people are queue jumping or something. And that really showed that the student had understood this abstract concept. And I didn't ask something to test it, I just asked them to relate it to their own lives. And I think that comes with the added benefit of if they relate it to something in their own lives, then I think it sticks with them deeper. As opposed to when we give them our examples and test them, then they put their maths hat on when they're in the maths classroom, and then they take it off with relief when they leave the maths classroom. Whereas if they relate it to things in their own life, then they start seeing things all around them, which is what I do when I notice a concept. So since that student said that about a non-order preserving function that is good for us, I've started noticing them all over the place, where previously I'd only noticed where they were bad for us. And so sometimes just that act of having conversations and asking them to come up with their own examples, I think shows how much they've understood the abstract concept.
Oh, that's very interesting. So I'm going to just ask one last question, and this is about your book, X plus Y here. So which is a lovely read. So and as your other books are, and early in this book you give this example. It's a sort of an abstract question, but coming really to the issue of gender equality that you also touched on in your presentation. And fairly early in the book, you give this example that if Alex has 7 cookies and Sam has 3 cookies, then how many cookies do we need to give to Sam so that we make sure that they have the same number of cookies? And on the surface, this looks like an easy question, but there are different ways to think about it. And could you give us just a short discussion of how you think about this in the context of gender equality?
Yes. If we were in an ingressive math class, then presumably the correct answer to that question would be we have to give Sam 4 cookies to make sure they have the same number of cookies. And one thing that is more congressive and more expansive, and I love how small children do this all the time, they always question the basic parameters of those kinds of contrived math questions. And so a small child is quite likely to say, well, what if they don't like cookies? Why do they need the same number of cookies? We're quite used to, if people are bigger, maybe they have more, they need more things than other things. Maybe they'd all rather have apples. Why are we giving them cookies in the first place? And I think we sometimes do this with men and women because we're stuck in the one-dimensional gender dimension. We say, well, men are better in these ways and we need women to become better in those ways so that they can be equally as successful. Instead of sitting down and going, why are we even rewarding that behavior? Why are we so determined that having self-confidence is important? Well, self-confidence is only important if we're in a hostile, ingressive environment. Why don't we create a more nurturing environment so that people don't have to have self-confidence? Because actually, I really like working with people who don't have self-confidence, because then they strive to improve at things. Whereas if we continue with the assumption that self-confidence is good, we end up with a whole load of arrogant people who think they're great even when they're not, and who end up doing things like running countries because they think they're so great at running countries even when they're not. And I think that this terminology has helped me to see things like that in the same kind of umbrella and in the same kind of light, and also to just rethink the questions I ask in class and think to myself, is this activity an ingressive activity, and how can I make it more congressive? Where previously we'd have to say, oh, is this an activity that appeals more to boys, and how can I make an activity that appeals more to girls? And that sounds really stupid, and it is really stupid, and it's how we end up with things like pink Lego and Barbie dolls with computer t-shirts, which doesn't really help anything at all. Whereas if we make more congressive activities, then we have more exploratory things, and we can even turn that question into a more congressive question. So instead of saying, how many cookies do we need to give to make sure they have the same number of cookies? We can say, you know, what do you think about this situation? Do you think this situation is fair? In what ways is it fair? How could we decide whether or not it's fair, and how could we make it fair in different ways? And what are some different ways in which it could be fair? And then it's much more congressive, it's much more exploratory, and I think it's much more inclusive, because it doesn't just go around saying, well, you're right, you're wrong, you're right, you're wrong. And I hope we all agree that in the world at the moment, we have too many ingressive arguments in which someone has to be right and someone has to be wrong. And I hope that we can have more congressive arguments in which we can just all explore and learn from each other rather than trying to put each other down. And I think that then we can learn more and progress more together.
Oh, that's very inspirational. Thank you very much, Eugenia. Unfortunately, we're out of time. I wish we could talk for much longer. And I hope one day that we'll be able to welcome you to Oz in person.
Oh, I hope so. I would love that.
Yeah, I know you've been here before, and so we look forward to being able to welcome you again.
Come back. Thank you so much.
So thank you very much. And thank you very much to all the participants and the listeners. And this lecture kickstarts ACEMS' many events celebrating International Women in Maths Day. Next week, on Wednesday, the 12th of May, we're proud to host the Road Ahead for Women in STEM panel discussion from 12 p.m. to 1 p.m. Australian Eastern Standard Time via Zoom. And so the details are available on the website. I hope you'll join us then. Thank you very much for joining us today. And thank you so much, Eugenia, for giving us such a fantastic insight into your ideas about X plus Y. Bye.
Thank you so much for having me.